Introduction, and I just want to say that we'll be taking turns giving the lectures, but the lecture course is a joint effort, and so if you have any questions on any part of the lecture course, you may ask those questions of either of us. You don't need to match the question to the speaker. So Sarah will be giving tomorrow's lecture and the fourth lecture, and I'll be speaking today and the third lecture. So the plan for this course is to introduce the theory of Euler systems, which is one of the main tools used to relate the values of L functions to arithmetical constructions. And the main emphasis will be on how you build and construct Euler systems. But today's lecture is an exception to that. So today will be about what Euler systems are and what they're for. So today will be about Galois representations and Euler systems. 2 will be a general toolkit for how you might build the cohomology classes that are the building blocks of an Euler system. And lectures 3 and 4 will be working out in detail 2 specific examples of Euler systems. So an Euler system is something you attach to a Galois representation. So I want to start by just getting a bit of notation and general ideas about Galois representations, how they come up, and what the interesting questions about them are. So I'm going to take K to be a number field. P at prime, which will be fixed pretty much throughout this course. And I'll take E to be a coefficient field, which will be a finite extension of QP. And we're going to look at representations of the Galois group of K on vector spaces over E. So rho from GK to the general linear group of V, where V is an E vector space. And all my representations will be finite dimensional. So GK here is the absolute Galois group. Of K. So there are an awful lot of these objects, and just to cut down to some that are really interesting and worth studying, I want to impose some basic hypotheses that will be in force for every Galois representation Sarah or I will ever mention. So rho is going to be continuous with respect to the natural topologies on either side. So GK is a profinite group, so it has a cruel topology, and this general linear group inherits a p-adic topology from the topology of E. So they're going to be continuous with respect to those natural topologies. And the second, slightly more subtle hypothesis is that rho should be unramified almost everywhere. So that means that rho should be trivial on the inertia group at V for almost all places, all but finitely many places V of K. So it's actually not that easy to construct examples of of rows that don't satisfy these conditions. Pretty much every natural thing that you write down is going to satisfy conditions 1 and 2. It's a good exercise to build one that doesn't. So a few examples. Firstly, something we saw already in Romyar's lecture, the cyclotomic character. So that gives you a character chi. This is chi p in Romyar's notation, but I have only one prime, so I'll just call it chi. So I'm going to take E equals QP for all of my examples. So this gives you a one-dimensional representation, and it's clearly continuous, and it's unramified outside the primes above P. So that's a very simple example. A slightly more sophisticated example comes from elliptic curves. So this is the construction of the Tate module. So if I take an elliptic curve over my field K, and since E is in use, I'm going to call it A. I'll define something with ZP coefficients first, and then I'll extend scalars to QP. Sorry. I knew I'd make that mistake. So from basic facts about elliptic curves, this is free of rank 2 over ZP, and hence VPA. Is a two-dimensional QP vector space with a continuous action of GK. And in fact, it's unramified away from P and the bad primes for the curve A. And a final example, which is in some sense a example covering just about all the other examples within it, comes from Ital cohomology. So if I take X over K, any algebraic variety, doesn't have to be smooth, doesn't have to be projective, or clearly it could be, so any variety. And this is important because it's a crucial distinction for what will come later. You take the base extension of this to the algebraic closure K bar. And then you get groups HI et al. Of XK bar with coefficients in QP, and these are Galois representations. And because you've extended to K bar from something that was originally defined over K, the functoriality of Ital cohomology tells you that these things have a Galois action. And they're finite dimensional over QP, and unramified outside some finite set of primes. Although it's a little hard to be precise about what that set is in this generality. So I said that that last example was somehow an example covering all the other ones. And I just want to give some notation making that precise. If we have a Galois representation V, we say it comes from geometry if it's a subquotient of my last example for some x. And I want to allow one slight extension to that. I want to allow twists by powers of the cyclotomic character. And the notation brackets j means twist by the jth power of the cyclotomic character. So all of my examples above come from geometry. I mean, one of them was the definition of coming from geometry. The cyclotomic character I've somehow built in by having this twist j, but in fact, Tate modules also come from geometry in this sense. So if you take the first étale cohomology, that's almost the Tate module, but you need to twist by 1. You should somehow think of the Tate module as being étale homology, so the twist straightens out the Galois actions to give you the cohomology. So in this course, we'll work a lot with Galois representations coming from geometry. And that won't be at the forefront in today's lecture, but from tomorrow's lecture onwards, we're really going to use the geometry, use the presentation of our Galois representation in the geometry of some specific variety to build interesting arithmetic, interesting cohomology classes for that representation. So that's just a hint at what's coming. So that was section 1.1 of the notes. So just to keep the section numbering compatible, this is section 1.2. I want to say something about L functions. So lots of arithmetic objects, like elliptic curves, give rise to an L function, and lots of them give rise to a Galois representation. And I want to explain how the L function is in fact encoded in the Galois representation. I'm working towards stating a conjecture saying that for any sufficiently nice Galois representation, it has an L function, and the values of that L function tell you something about the arithmetic of V. So I need to tell you how to recover the L function from V. So V is an unramified prime for big V, so that is a place where the inertia at V acts trivially. So I'm going to define a polynomial. So T is just a formal variable. This is called the local Euler factor of V at the place V. That's going to be the determinant of an E-linear operator. Which is 1 minus t times the inverse of the arithmetic Frobenius acting on V. So the Frobenius is only well defined up to conjugacy and up to the inertia subgroup, but because inertia acts trivially at V, this is a well-defined endomorphism of V up to conjugacy, and we can take its characteristic polynomial. So this is a polynomial in the variable t of degree equal to the dimension of V. And we can extend this definition to the bad primes as well. But for the primes above P, which are clearly going to be the hardest, we need some local properties, which are guaranteed for representations coming from geometry. So we have PV defined for all finite places of K, although I'm not going to tell you how for the bad places. And we could define this formal product, the product of these polynomials evaluated at the norm of v to the minus s, inverse. So this is cooked up so that the Riemann zeta function is going to be a special case of it. And more generally, for any number field, you get the Dedekind zeta function. V is an E-vector space. So I'm specifying that I'm taking the characteristic polynomial thought of this thing thought as an E-linear operator. Obviously, if E is a quadratic extension of QP, then an E-vector space is also a QP vector space of twice the dimension, but characteristic polynomials are different. So I'm just specifying that it's characteristic polynomial with respect to this particular choice of base ring. Maybe I'm being pedantic, but I wanted to make that clear. So again, this is a nice consistency check that you've understood the definitions. For the trivial representation, what you get out of this is the Dedekind zeta function. So something a bit miraculous has occurred here, because a priori, these polynomials have coefficients in some finite extension of QP. So I'm implicitly fixing an isomorphism between E bar and C, and then taking my infinite product in C. And it's somehow weird and miraculous that this gives you anything interesting whatsoever, but in practice it does. And another example of this, if you take not the Tate module, but this twist of the Tate module, the first étale cohomology for an elliptic curve, this definition of the L function again gives you something with something reasonably sensible. It gives you the Hasse L function. So as we know, the values of both of these L functions that I've mentioned are very much bound up, or expected to be bound up, with arithmetic. And I'm going to tell you how to extract from V the thing that these L functions are expected to govern. So that will be the analytic side of a conjecture, and now I'll give you the algebraic side. Sorry, one thing I should have said, which is in my notes, but I almost forgot to say. This thing is, for V coming from geometry, you can show it's convergent in some right half-plane, but it's conjectured that it has meromorphic continuation and a functional equation. Yeah, so we can talk about its special values. We have some meaningful thing to evaluate, even outside the domain of convergence. So this conjecture is expected to be extremely hard. Yeah, so as I was saying, the algebraic side of the theory now. I've told you what I mean by a Galois representation, and there is a cohomology theory for these things. One has to be a little careful finding references for this sort of thing, because a lot of introductions and texts on Galois cohomology are written very focused on the requirements of class field theory, so tend to assume that the modules are some big discrete groups. But here we're going to be working with continuous actions on p-adic vector spaces. But the theory still does work. So you have groups, indeed E-vector spaces, hi of kv. And we're mostly going to be interested in H0 and H1. H2 also exists, but for I bigger than 2, these things are 0. So the zeroth cohomology is what you obviously expect it to be. It's just the invariance. These pens are slightly bigger than I thought they were. So this is the quotient of cocycles modulo coboundaries. I'm sure all of you have seen this definition many times before. But I just want to write it out to emphasize one particular aspect, which is the continuity condition. I'm not taking abstract group cohomology. I'm using the fact that my representations are continuous and taking a cohomology theory that reflects that. So it's cohomology defined by continuous cocycles. So it's not that easy to find an example where the continuous cohomology and the abstract cohomology are different, but they do exist, and it's quite fun finding them. But it's the continuous cohomology that turns out to be related to arithmetic in a nice way. So these groups have lots of nice properties, but they are not, in general, finite dimensional. For a number field K, the cohomology is simply too big. And just to give you an explicit example of how that comes up, you can see it using the Kummer map. So I take the representation that's the trivial representation twisted by the cyclotomic character, and then we have a map which goes from K cross tensor with QP. I'll call this map little kappa, the Kummer. And this map's actually injective. It's almost an isomorphism. The defect of it being an isomorphism is just that you need to periodically complete on this side. But in particular, it's injective. And this guy, for a number field, is an abelian group of countably infinite rank. So obviously this thing can't be finite dimensional if we're putting countably many copies of QP inside it. And there's a similar construction for elliptic curves if you replace QP1, which is somehow the Tate module of the multiplicative group, with the Tate module of an elliptic curve. But that won't play a major role in what I'm doing. There's a little more about it in the notes. So if we want to study these things and make conjectures relating them to values of L functions and generally get somewhere with them, we need to cut away some of the junk, get rid of the noise. So what we want to do is to cut these cohomology groups down to something that's finite dimensional and that we can then home in on and study. So what we're going to do is we're going to impose conditions locally at each prime. So a local condition for V at a prime V is just going to be any subspace of the local cohomology group. So you can take Galois cohomology for local fields as well. And these groups, the cohomology for the local Galois group, these are finite dimensional. So what we're going to do, we're going to cut our cohomology groups for the global group down to size by looking only at things that land in some nice subspaces when you localize them at every prime. So what are the kind of subspaces we can consider? So there are some boring examples. You can take the zero subspace, certainly a perfectly legitimate choice. And I call this the strict condition, because we're going to require that some class lands inside a subspace, and the smaller the subspace is, the stricter this condition is. So this is the strictest condition you could impose. And at the opposite end, you have the relaxed condition. So you take FV to be the whole of the local cohomology. So all of H1 KVV. But there are some more subtle ones. And these are the ones that are going to give us some interesting control on the cohomology. The unramified local condition. Let me just put some notation on these. So Str for strict, rel for relaxed, and UR for unramified. And these are going to be the cohomology classes that become trivial when you restrict them to inertia. And this is somehow the Rolls-Royce of local conditions, the best local condition for a prime that doesn't divide P. And for V divides P, it was, I think, a bit of a mystery for quite a while to find the right analog of the unramified local condition. Because the trouble is that the unramified local condition for V divides P tends to just give you 0. So the correct analog turns out to come from Fontaine's p-adic Hodge theory and was written down by Bloch and Kato. And here you need to assume that V divides P and big V has some nice local property which is guaranteed if you come from geometry. So Fontaine defines some huge ring B Chris with an action of GQP, and you look at the kernel of this H1 to H1, tensor it up to this huge ring. So I'm afraid it would be a whole lecture course in itself to explain why this is a good definition, why it gives you something interesting, but there's a brief hint at what the definition is. But this is the right local condition to consider at V dividing P, as we'll see in a moment. So I'm now going to define 3 subspaces of the global cohomology of V. And these are called the Selma groups. Perhaps I'd better do this on a new page. So the relaxed Selma group is the global classes whose restriction to primes not dividing P land in this unramified local condition space. And at the primes dividing P, I require they land in the relaxed local condition, which is just a vacuous assumption, because that's the whole of the local cohomology. So that's the largest of my three spaces. And then I'll define cell blockato of KV and cell strict of KV to be the same, but with the appropriately chosen local conditions at primes above P. So, as will become clear in a moment, the important guy here, the one we really want to study, is the Blockato-Selmer group. This turns out to be the right thing to formulate a conjecture relating L values to Galois cohomology. You should think of the strict condition and the relaxed condition as somehow a crude upper and lower bound for the Blockato condition. They're somehow approximations to it that you can get without having to do hard local theory at primes above P. So that will become clearer in a moment when I start talking about the key construction of these lectures, the Euler systems. But I'll just give an example of what these look like in the context of Kummer theory. So we had this map sending units into the global cohomology. So we can characterize the Selmer groups according to which units land, which elements of K star land in those Selmer group subspaces. So the relaxed Selmer group, you see exactly the things in K star that are units away from the primes above P. So that gives you an idea that we've chosen the right local condition at the primes away from P. So we've trimmed down to things in K star that are units at those primes, but we've somehow not done the right thing at P yet. But if you do the Blockato guy, you get exactly the right answer. You get clearly the thing you want to study in this case, which is the global units of K tensored up to QP. So the Kummer map identifies this group with the Blockato-Selmer group of QP1. And just to link back to something we've heard about in the earlier lectures this morning, what's the strict Selmer group? Conjecturally, it's 0. And that conjecture is precisely Leopold's conjecture. The precise statement here is that the strict Selmer group is exactly those ZP linear or QP linear combinations of units that die when you map them to the local units at P. So it's the kernel of this map from EK to E bar K from John's lecture. So now we've got an analytic object, the L function, and we've got an algebraic object, the Selmer group, attached to any Galois representation coming from geometry. And what I'm going to state is a fairly crude form of the conjecture, but it's already one that's very rich and interesting. If you take the dimension of this Selmer group, which is known to be finite, I should maybe have pointed that out. So these are E-vector spaces, and the theorem due to Tate is that these are finite dimensional. By trimming down to classes that satisfy nice local properties, at least at the primes away from P, we've got a finite dimensional space. And now this conjecture is predicting the dimension of this space. And there's a correction term. So this is something coming from H1, this is something coming from H0. So you should think of this as being a bit like an Euler characteristic. And the conjecture is that this is given by the order of vanishing of an L function. There's a duality game going on constantly in this theory. So the L function you have on this side is the L function of the Tate dual, V star 1. And that is expected to be related to the order of vanishing of the L function of V, but there are various Archimedean gamma factors in the functional equation. So you end up with all sorts of awkward correction terms. But this is the cleanest statement I know of the rank part of the conjecture. So the actual conjecture predicts much more. It predicts a relation between the leading term of this guy and the determinant of some height pairing on this. In the simple case where the analytic rank is 0, it relates the value of this to the order of a finite group version of this defined using lattices. But this one is enough to be going on with. This is a very difficult conjecture. And what we're going to be outlining later is how you can prove some cases of this conjecture. So for trivial representation, this is true. So you can compute the Selmer group using class field theory. It turns out that this is 0. This obviously is minus 1. And here you hit the pole of the Dedekind zeta function of k. So what it tells you is that the fact that the Dedekind zeta function has a simple pole confirms this conjecture. So this is maybe not very deep. For the first Tate twist, however, something a bit more significant is happening. We know what the Selmer group is for QP twist 1 in terms of the unit group of k, and you can compute the order of vanishing of the L function because you know what the Archimedean gamma factors are. And it turns out this conjecture precisely recovers the formula of Dirichlet for the rank of the unit group. So R1 plus R2 minus 1. And for elliptic curves, this is close to, but not quite the same as the rank part of the BSD conjecture. So the Selmer group, in this case, is almost equal to A of k tensor QP via Kummer theory, but there's a correction term, which is, the co-rank of the P part of Shah. So if you already know that the P part of Shah is finite, this is exactly the rank part of the BSD conjecture. And without that, it's somehow the closest you can get to the BSD conjecture purely in terms of Galois cohomology. So now, the last few minutes of the lecture, I'm going to introduce the main actor in this drama, which is the notion of an Euler system. So for simplicity, I'm just going to take my representation to be a representation of the absolute Galois group of Q. And you can do this more generally, but it becomes more awkward. And even though V starts out as a representation of GQ, you can take the Galois cohomology of it after restricting it to any number field. And there are relations between these and the key construction I need here is the norm map. And that's going down. It takes a cocycle or a cohomology class for the Galois group of L and norms it down to something for the Galois group of K. And I'm going to fix a lattice inside V. This is technical but important. And then you have cohomology and co-restriction maps for T in place of V. I'm going to fix a set of primes that I declare to be the bad ones, which will include P and all the primes where V ramifies. Now, usually, interesting Galois representations coming from geometry tend to be massively ramified at P anyway, but even if not, I'm going to assume that P is in this set. Sorry? It's the coefficient field. V is an E vector space. I'm going to want to control denominators, so I want things to land in a lattice inside V. So it's going to be a collection of guys Cm, indexed by integers at least one, where Cm is a cohomology class for T over the mth cyclotomic field. And there's got to be some relation between these, which is why I gave you the co-restriction maps. And if L is a prime number, I can compare CML and CM. What I'm going to ask for is somehow in the bad cases, this is just going to be Cm. But in the cases where I'm adding a new prime and it's a good prime, so L isn't in sigma and L doesn't divide M, you have the Euler factor, but not a V, a V star 1, with the Frobenius element in the finite group that acts on this cohomology. And this is well defined because L doesn't divide M. So I want that operator acting on Cm. So that's the definition. It's not so hard to write down, but it's much, much harder to see why it's a natural thing to define. So why would one want to study this class of objects? So I'm going to give an example in a moment, but the key reason why we want to study these is because they're useful. If you have one of these things, you can use it to control Selma groups. So here's the basic theorem in this area. In this form, it's due to Rubin, that it was somehow an abstraction of work of Kolyvagin for a specific example of a V and an Euler system. If you have an Euler system for T sigma, for some lattice T and some reasonable set sigma, the conclusion won't depend on T and sigma, and the bottom class, the class over Q in this collection, is not 0, and there are some hypotheses. My technical conditions are going to be strong enough to force the cohomology to be torsion-free. So the technical conditions are that the image of Galois in the automorphism group of T be really large. And that in particular forces the cohomology to be torsion-free. So Sarah was pointing out that this theorem is stated in Rubin's book with the assumption that C1 be non-torsion, but I can just fold that into the technical conditions. So the strict Selma group under these hypotheses vanishes. So if you want to prove the Blockato conjecture, you want to know something about the Blockato Selma group, but the difference between the strict Selma group and the Blockato Selma group is something purely local at P. This gets you almost all of the way to understanding the Blockato Selma group. So Kolyvagin used this to prove the Birch-Swinnerton-Dyer conjecture for, the rank part, for elliptic curves of analytic rank 0 or 1, and it's been used in a number of other works recently proving cases of Blockato. So I have a few minutes left, I think, so I'll just quickly explain one example of an Euler system. And this is the Euler system of cyclotomic units. So here, my representation V is going to be QP1. And I'm going to take elements in Q mu m star, the various m, and then just transport them via the Kummer map. So we can't quite take Cm to be the Kummer image of Um. The problem is that Um doesn't know what P is yet. And so you get Euler factors at all primes, including P. And you don't want that, because the set sigma has to contain P. Unfortunately, that's scrolled off the previous pages, but it was there. So we modify it very slightly. And we define a new unit, and if P divides M, this is actually the same as UM, but it's slightly different if P doesn't divide M. What we've done is we've killed the Euler factor at the prime P. This is an Euler system for T being ZP1 and sigma being just the set P. So I only maybe have time for one more remark. I'd hope to say a little more, but I'm running short on time. This is something I'm dropping in so Sarah can use it in the next lecture. It's that Euler systems can be twisted. If you have an Euler system for V, you have an Euler system for every Tate twist of V. So this is sometimes called the Soulé twist. And we're going to use this in building Euler systems to say that if we want to build an Euler system for T, or for V, maybe that's difficult, but it's easier to do it for V twist 7, and then we just work with V twist 7, and then we twist back again. So this will be useful in building Euler systems via geometric techniques later. I think I was probably actually supposed to give a 50-minute lecture, and I think I've given a 55-minute one, so I'll stop there. Thank you.
Questions?
Thanks. So, sorry, for the statement of block-Kato conjecture, is there any restriction on the representation V, or this is for any representation V?
It's for any representation coming from geometry. I'm just trying to find the appropriate page.
So in particular, the periodic Hodge condition at P is just de Rham.
Yes, just de Rham.
Okay, also, could you... yes?
There are various versions. This remark is addressed to people who've encountered a bit of periodic Hodge theory. There are three slightly different flavors of the Bloch-Kato-Selmer condition, H1E, H1F, and H1G. And I'm using H1F, and that turns out to be the right one to use for any de Rham representation if you're using the L function with its Euler factor at P. If you strip away the Euler factor at P, that corresponds to using H1G. Does that answer your question?
Yes, and there's no, just to confirm, there's no restriction on how this representation is ramified at places away from P. It could be,
No, there is no restriction, because the unramified local condition, as I've defined it, picks out the right part of the cohomology, the correct part of the cohomology, even at ramified places away from P.
Sorry, could you also, in the last slides where you stated the theorem of Rubin, could you say just in words what the technical conditions are?
I'm tempted to respond with the technical conditions are the ones given in section 2.2.4 of Rubin's Euler systems book. If I try and do this from memory, it's almost certain that I'll get it wrong, but basically the conditions are that the action of Galois, the image of the Galois group in the automorphisms of T should be large. It should contain elements satisfying certain conditions. So in particular, T should be irreducible as a well, V should be irreducible, and there should be an element in the image of Galois whose co-kernel is free of rank 1. So for instance, for an elliptic curve, for almost all P, the image is GL2ZP, so that's easy to get. So it's a large image condition.
All right, so maybe in view of the time, we'd better postpone questions to lunchtime. Let's thank David again.